Good evening. Tonight we have Anwesha Sahu talking about shy, unpredictable and greedy stars. Anwesha is an accomplished astrophysicist specialising in giving talks about cataclysmic variable stars, called CVs, and radio astronomy techniques. Currently pursuing a PhD at the University of Warwick, she delves into the dynamic and intriguing phenomena of the cosmos, contributing to the scientific community with her research and insights. Beyond her academic pursuits, Anwesha is an avid guinea pig enthusiast and a dedicated fan of Taylor Swift. Her multifaceted interests reflect her vibrant personality and a passion for science and the arts, whether unraveling the mysteries of the universe or enjoying the latest Swiftie hits. Anwesha brings enthusiasm and excellence to everything she does. Thank you.
Thank you very much for the kind introduction. That was really nice. Thank you. I'm really happy to be here today and to be able to share more about what I do and the research at Warwick with you today. Yeah, I'm happy to begin whenever you're ready.
When you're ready.
Oh, perfect. Yeah, so as mentioned previously, I will be talking about my research work today, and hence I have titled the talk today as Shy, Unpredictable, and Greedy Stars, which are indeed the stars that I work with. So hopefully by the end of this talk, you will know exactly why the stars that I deal with are cataclysmic variable stars and AMCBN type stars are shy and greedy. Before we delve into the deep end of the spectrum with more physics, I thought I'd introduce myself a bit more along with some of my favorite things in the world. So here in the top left corner, just a quick question. Can you see my cursor when I point at things?
Yes, we can.
Excellent. So right here, what we have is we have a binary star system, and a binary star system is when you have two stars which go around each other. If they're close enough, and if one star is more massive than the other, then that star will start quite literally stealing material from the lighter star, distorting it in the process. And as it gets or accretes all this material onto itself, we will be able to see jet emissions from it across the electromagnetic spectrum. That is part of what I study, and I focus especially on the radio wave end of the electromagnetic spectrum. That leads me very neatly onto this picture here in the bottom left corner, which is of a radio telescope array called the Very Large Array. And this is in New Mexico in the States. So the way that radio telescopes work is we don't have just a single telescope, we have 27 telescopes in this case, and they all help produce a single image. I'll delve more into the physics behind radio interferometry towards the end of the talk today. That then brings me to another part of my PhD research, which is into the field of transients. And transient astrophysics is essentially a study of anything in space that is, as the name suggests, transient. Most of the time, this refers to really rapid, sudden optical brightenings that we observe through telescopes, such as supernovae, which is when stars blow up, or really massive stars blow up towards the end of their life. And this supernova right here, you might have seen it in the news a couple of years ago. This occurred in a galaxy not too far away from ours called the Pinwheel Galaxy. And this supernova was incredibly bright, and it even outshone the light of the galaxy combined. So supernovae are extremely powerful sources of energy in the universe, and I look into classifying these supernovae through a process called spectroscopy. In addition to my research work, as stated in the introduction, I absolutely love guinea pigs. Here are some pictures of my two guinea pigs who are currently running around the house because I let them free roam in the evenings. And this one here is Barry, and this is his brother Paul. And they're both about 2 years old, and they help me work from home when I'm doing my research from home by keeping me company, and I like to think that they understand physics because I babble a lot to them. With that being said, we're going to get into the contents of today's talk. So I'm going to talk about how CVs can be made. And no, these are not the job kind, so we're not talking about resumes here. We're talking about cataclysmic variable stars. In short, we call them CVs in the community. So we're going to look into how these binary star systems form and why they're so important to us. We're going to look into the steps involved in making a supernova, which is when a star blows up at the end of its life. And we're going to look at potential connections between CVs and supernovae. Could CVs potentially lead to supernovae? And what kinds of common things do they have? That's one of the key bits of research that we do at Warwick as well. Lastly, I will delve a little more into what I do, more specifically in my day-to-day work with the PhD, and I'm going to talk a bit more about why I decided to give 4 years of my life to weird things. Still got 3 more years. Perfect. So the first step is how to make a CV. So a CV is, as mentioned previously, that is a cataclysmic variable star system. This means that we have 2 stars in a binary pair orbiting each other. Now, before we get to the details of the dynamics of this binary star system, let's take a look at what are the exact ingredients that we need to form such a system. So, to make a CV, what we need is a white dwarf star and a low mass main sequence star. So we're going to go through this diagram that I have here on the right to figure out how we can get to each of these stars. So all star systems, they start off as massive clouds of gas. Now, if this gas gets some kind of disturbance in the form of, radiation or some kind of shock wave that hits a cloud of gas, then this giant gas cloud that starts collapsing and it forms this protoplanetary disk. Now, this protoplanetary disk has a very hot center, and eventually the gas within that disk starts piling up in the center, and that leads to the birth of a baby star. Depending on the mass of this initial protostar, that star can evolve as either a low or medium mass star like the Sun, or as a highly massive star. Now we're going to focus on the upper branch today because that's what we use, or that's what happens when you want to get to the 2 types of stars which will be in a CV. Now, because the 2 stars will not necessarily have the same amount of mass, that means that one star might evolve faster than the other. So let's take the case of the star that is evolving faster. That star will go through its main sequence phase, such as the Sun, and it will evolve into a red giant first, eventually shedding off all of its outer layers towards the end of its life, and then all that will be left behind will be the cool core, extremely dense core in the middle of this planetary nebula called a white dwarf. Now, while all of this is occurring, that second star in the system is still evolving. It hasn't quite reached the white dwarf star yet. So just to reinforce the point, by this stage we already have a white dwarf star, but we don't yet have a second white dwarf star because the second star is still evolving. So as the second star evolves, it gets to the red giant phase, and we're going to hit pause right there. So as that second star has now evolved the red giant phase, what we now have is we have a white dwarf star and a red giant star, as we can see in this upper panel in this image over here. Now, one of the most important laws of physics is the conservation of momentum, which states in simplest terms that the overall energy of a system remains constant, and there's some fun physics that goes on, especially when systems are orbiting each other, and that is known as the conservation of angular or orbital momentum. So what happens is that as these 2 stars are orbiting each other, one as a white dwarf and one as a red giant, the two stars come closer and closer to each other. Now, each star right around it, it has something called a Roche lobe. Now, this is a mathematical construct, but we know that it exists in the physical sense because we have had indirect detections of these. So a Roche lobe is a region around a star which is such that if a star is close to another star and it fills its Roche lobe region such that the end of the Roche lobe of one star hits the center of mass of both the systems. So right here we have the Roche lobe of one star, and here we have the Roche lobe of another of the red giant star. And here we have the center of mass. So when the Roche lobes intersect at the center of mass of the two systems, we can get something called a common envelope. What that means is that the outer atmospheres of both these stars appear to merge. So the mass from the less massive star, which in this case is the red giant star. So this is a bit contrary to expectation because it's the bigger star, so we might expect it to be more massive or heavier. But in reality, red giant stars are really gentle giants in the sense that they're extremely puffy, but they're not that massive. So they don't have as much matter in them, but the matter in it is really just really puffed up, kind of like candy floss. And that's what's happening here. So the matter from the red giant star has now started seeping into the Roche lobe of the white dwarf star, and they have a common envelope. And this is what we see as in this kind of sideways bowling pin shape right here. That is our common envelope stage, which has occurred through a process called Roche lobe overflow. So Roche lobe overflow is when a donor star, such as this star, literally gives away its material to the more massive star, in this case, which is the white dwarf star, through essentially the force of gravity. So in this diagram right here, we can see a bit more clearly exactly how the process of Roche lobe overflow works. So here we have our accretor, or the white dwarf star. Right here, we have got the center of mass of the two systems. As astrophysicists, we refer to this as the inner Lagrangian point, L1. And this right here is our star, our donor star. So here we can see very clearly that the Roche lobe is this teardrop-shaped or deformed circle shape which exists around both the stars, which allows matter to be transferred from the donor star here onto the binary companion. Now, once it has once the stars have evolved past the common envelope stage, if there's still matter transfer occurring, we get something called an accretion disk. And this accretion disk, as stated in the diagram, that is the gas stream that is formed because of the matter from this giant star being quite literally drawn into this more massive star. This accretion disk is indeed what we can observe optically through our telescopes, and that is what gives us most of the information of these systems. So when we observe cataclysmic variable star systems with our telescopes, we don't actually see two separate stars because these two stars are extremely close to each other, which means that our telescopes are not sensitive enough to be able to resolve two sources like this. But what we see most clearly is a blur and the presence of this accretion disk, because when the stars are undergoing accretion, the accretion disk can emit something called jets, which is radio emission, and this radio emission is what we detect, and we can then deduce that indeed what we observe is a cataclysmic variable star system. So now we have seen how we can make a cataclysmic variable star system. And just remember one more key thing before we move on to how to make a supernova, and that is why these systems are in fact called cataclysmic and variable. So when we see that matter goes into the accreting star right here, what happens is that this gas and dust, which accretes or deposits on top of this more massive star, sometimes it gets really concentrated around specific regions. And as we all know, when gets extremely hot, such as that in the sun, then the gas can literally ignite. And what we get is something called thermonuclear runaway or a thermonuclear fusion reaction. That very process is extremely energetic and releases a bright flash of light. And that increases the brightness of that entire cataclysmic variable star system by several orders of magnitude. As a result of that, we can detect this optical brightening using our telescopes through something called light curve analysis. So, what that means is that we look at the amount of light we receive on our telescopes from this star system like every single day. And when we have an outburst, which is when we have the thermonuclear explosion on the surface of the star, we get a big spike in the amount of light that we receive. And that spike tells us that, okay, there's been an outburst now, and we can get any follow up observations from that. That explosion itself is highly cataclysmic, hence the name cataclysmic variable, and variable because these outbursts change or vary the brightness of the star system. Right. So with that, now we're ready to see how we can make a supernova. So supernovae are manifestations of the end of the life of extremely massive stars. So there's several different types of supernovae. One of the most common supernovae that we see are type 1a supernovae, but in most popular science books or documentaries that we can come across often, they refer to type 2 supernovae, which are core collapse supernovae. So core collapse supernovae is when you have stars which start their lives off as over 8 times the mass of the sun. So by the time that they get to the end of their lives, they have burned through all their hydrogen and helium. They will have produced carbon, oxygen, burned through those, created silicon and magnesium through fusion following that, burned through all of that, and then their core will have iron. Now, iron cannot be fused any further, and as a result of that, the star collapses on itself and leaves behind a neutron star or a black hole, depending on the final mass of that core. Now, that is called a core collapse supernova. But over half the supernovae that we observe in the universe, they are all type 1a supernovae. And type 1a supernovae are supernovae which we think as of now to be the result of thermonuclear runaway, which is the process that I explained previously, which is what happens when you have fusion occurring or when you get extremely hot gas that literally ignites or blows up the star. So, despite type 1a supernovae accounting for over half of the supernovae that occur, we still don't have definite answers as to what causes them. Hence, this is one of the leading fields of research in astrophysics, and we have a massive team at Warwick that looks into supernovae. So, in type 1a supernovae, one of the key theories or for the progenitors of these systems are binary white dwarf stars. And these stars are called AMCVN systems. So, but AMCVN systems are when you have two white dwarf stars. So, when a CV evolves even further, so the second star, which was a red giant, has now become a white dwarf star. When you have two white dwarf stars going around each other so that they orbit each other once between every 5 minutes to an hour, so really rapid orbits, those star systems could be progenitors for type 1a supernovae. And that's because eventually, due to the laws of angular momentum conservation, these two stars will spiral towards each other. And when they run into each other and they collide, that could be a thermonuclear runaway leading to a type 1a supernova. Or if one of the stars continues drawing so much material from the donor star that that gas heats up and literally ignites one of the white dwarf stars, that could also lead to a type 1a supernova. So we've got these two theories. Now, the white dwarfs that we're concerned with here, those are going to be mostly carbon and oxygen, hence the CO white dwarf binaries. Now, there's a key physics or astrophysics concept that comes into play when we're dealing with white dwarf stars, and we want to distinguish that between the formation, between what causes a star to form either a white dwarf or a neutron star or go supernova, and that is the concept of the Chandrasekhar mass limit. And this, in fact, is what led the astrophysicist Chandrasekhar to get the Nobel Prize several decades ago, and this was because he, through his findings, was able to deduce that for a star to sustain itself as a white dwarf, it must have a mass of the core of the star at the end of its life should have a mass that is less than 1.4 solar masses. If it has a mass that is higher than 1.4 solar masses, that will result in the star collapsing further so that it can turn into a neutron star. Or if it's even more massive than, if the core is even more massive than 3 solar masses at the end of its life, it will turn into a black hole. So we did a lot of observations for this, and to date, we have not observed any white dwarf stars which are more massive than 1.4 solar masses as predicted. And that has led to a Nobel Prize in physics. So one of the best tools at our disposal to study supernovae and to study CVs is a process called spectroscopy. So I'm going to dive into a bit more detail now about the actual observations that we do. And spectroscopy is when we take light and essentially pass it through a prism, or we pass it through a slit, so diffraction gratings, or we pass them through a combination of both. So if you have a diffraction grating and a prism, astrophysicists are very, very clever when it comes to making words up. We call that a grism. So a grating plus a prism gives you a grism. So we use combinations of these, and we can split the light that we get from these deep astrophysical sources to be able to see all the different components and their intensities at specific wavelengths. What I show you here in these figures here are from actual supernovae that we observed in some observation runs over the last couple of months. So these data, they were obtained using the new technology telescope, which is located on a mountaintop in the Atacama Desert in Chile. And using the grism at this telescope, we were able to obtain spectra for several supernovae. We ran that through our program to identify all the different peaks, so the intensity of the different wavelengths that the light from the sources would emit. And we then cross-matched these with templates for different supernovae that we have observed in the past. So what we see here is the software or the program's predictions as to what type of supernova it could be. So we run through several of these models, and for this particular supernova here, the best match was to a type 1a supernova. And we can see that most of the red lines, which is what the model had, they match with the observations as shown with the white line here. Now, to give you a better idea of how this model works, and why it is very important to check our model and our observation with multiple templates. Here we can see an example of a terrible match, a very poor match, as almost none of the peaks seem to correspond with our actual spectra, which is in white. So spectroscopy is how we go from just detecting a bright spot in a frame from the telescope image to figuring out exactly what type of supernova we're dealing with by studying the wavelength and the intensity of the supernova at different wavelengths, because each of these different wavelengths corresponds to a specific element that would have been produced and emitted when the star went supernova. So what I am doing is a combination of all these three fields of research. So we're going to now combine CVs, transients, and AMCVNs, which are the binary white dwarf star systems, and we're going to see how we can use radio astronomy to study all of these. So in the middle here, we have a picture of one of the telescopes that Warwick has played a leading role in constructing and is maintaining. This is the gravitational wave optical transient observer, which is located on a mountaintop at La Palma in Spain, in the Canary Islands. And what this telescope does, so the short form of the telescope is GOTO, is it scans the night sky every 4 days. So it scans literally every inch of the night sky every 4 nights, and it then compares the images of each of these regions with a previous image taken on a previous night, and it looks for differences. This process is called difference imaging, and the goal is to find that if there's any region which appears brighter than it did a few nights ago, that means that we could have detected a transient, which will allow us to then do further spectroscopy to figure out what exactly is that object. Is it a CV or is it an event like a supernova? The first detection for that is using photometry and difference imaging, which is done with GOTO. Now, this particular setup is GOTO North because we have that in the Northern Hemisphere. We have an identical setup in Siding Springs in Australia, so we can cover the entire sky around the Earth, not just the Northern Hemisphere, but also the Southern Hemisphere. So what we can do with radio astronomy is study these systems at the radio wavelengths. And radio astronomy is inherently different from optical astronomy because whereas in optical, we can literally just point a single telescope with a few lenses at the source and observe it, radio waves have far much longer wavelengths and they can be much fainter to detect. So what we would like to do is we have arrays of radio telescopes. So this is the VLA, which has 27 radio telescopes arranged in a Y-shaped configuration in the New Mexico desert in the States. And what these telescopes do is they look, all of these telescopes will be pointed at the same source in the sky. All of them will collect light through interference, which is what we can see here. So if we pass light through two different slits, they can get to the same point, but they will be shifted by a specific number of wavelengths, which is what's going to happen because all of these individual telescopes are sort of located slightly further apart from each other. What we then do is we combine the signal from each of these telescopes in a process called interferometry. We then do some filtering and noise reduction because we know that all satellites and communication devices operate at radio frequencies, and what we're left behind is with a beautiful image which shows all the radio emissions in that system. So this image that we have in the top left, that is a picture of the Milky Way galaxy in optical wavelengths. And this image that we have in the bottom right, that is the exact same image, but this time in radio wavelengths as observed by the Meerkat radio telescope array in South Africa. And what we can see is far more detail than we could have seen with optical. And these regions which appear darker, that's where we have radio emissions, so we can figure out a bit more about the physical mechanisms which lead to this, as well as uncover a lot of phenomenon that we don't quite understand. Like up until now, we don't really know why we get these filaments, and that is a very active area of research. This brings me to the final slide of my talk today, and I'm going to summarize everything that I have that I have spoken about today. So essentially what we have seen is that with radio observations, we can constrain or reject models for the physics of jet emissions and accretion. So we can study how stars steal material from donor stars through the process of accretion, because while they are accreting material, they emit radiation in the form of radio waves that we can detect on Earth. As we understand these accretion models using jet emissions and radio emissions, we can understand what could be the causes behind type 1a supernovae, which are the most popular kind of supernovae that we observe in outer space. And if we did that, we would have answers to one of the biggest questions in modern astrophysics. Finally, I would like to bring your attention to these two projects here, where you could help out astronomers and contribute to real research that is ongoing right now, because one of the main challenges we have in astronomy today is simply the amount of data that we generate each night. It is absolutely humongous, and we would not be able to process all that data without citizen scientists like you. So this project here is called Kilonova Seekers, which was developed by one of my colleagues at Warwick, Tom Killestein. And what this project seeks to do is when you go to this link, you will have the chance to go through a training which will equip you with the skills to look at an image that was taken by GoTo in the previous night, and you will be able to determine whether that image or that bright spot that you see in your frame, whether that is a real transient, so whether it's a real supernova, or whether it's just noise and accidental brightening. And with that, what we can then do is at Warwick, we will be able to get those images that you have essentially vetted and said, okay, this is a real image, and we can then do follow-up studies on that. And up here, we've got the friendly virtual radio interferometer. If you want to have a go at radio interferometry yourself, you can check out this link here, which will take you through some of the basics of how we can convert between optical and radio images. And with that, I will end my talk there, and I'm happy to answer any questions you may have. Thank you.
Anwesha, thank you very much. What a fascinating profession you've worked in. Can I ask you to stop sharing your screen?
Yeah.
And then we can see all the usual suspects. And if I just turn that to gallery, as usual, ladies and gentlemen, if you're online and you've got a question, will you put your hand up? I'm going to try and get a view of the room for you. We are having trouble with our that. You see most of the yes, we can. You see most of the usual suspects there. So we'll welcome one of our Spanish correspondents, Trevor Worrell. Trevor, can we have your question, please?
I'm open not to agree, but first of all, thanks for a fascinating presentation. I've got 4 hopefully quickie questions to ask, and 3 of them around that L1 point. I just wondered what the size of that L1 point is, diameter-wise, for it, you know, to take that material across from the donor star. Maybe the speed of transfer, and when does it stop? When does the feeding stop? Does the donor star have to get to a much smaller mass and then it just breaks off? That's the first 3 questions.
So the L1 point, it's not a fixed distance from a star. So any binary star system that we have, every such system will have a different L1 point, and there's several factors that play into this, such as the mass of the star, the density of the star, and the original distances between the stars. But on a rough order of magnitude, if I were to make an educated guess, that would be around several hundreds of radii of the larger star's core. So around several atmospheres across. That's where L1 would roughly be.
I
Can I
was
ask you to repeat your second question,
yeah, sorry.
please?
It
Thank you.
was really the diameter because I could see the donor star being sucked dry of its material. I'm thinking, well, is this like just a contact point, you know, an infinitely small point where it transfers across, or something much grander? That's related to that first question, yeah.
Yeah. So essentially, what we have is we have like a funnel-like transfer occurring rather than a kind of like a fuzzy cloud. So that's when the stars are just about in contact. So this is before they have the common envelope stage. If they're much closer than that, then they would have a common cloud of gas surrounding it, but this is not that case. So if you just have simple accretion occurring across the Roche lobe and through the L1 point, it is very much like a funnel-like accretion that occurs. Yeah.
Yeah, I could just, and that went on to the second question about the speed of transfer. I could almost imagine the smaller the funnel, the more rapid the transfer takes place.
Mhm.
So the final bit is when would the feeding stop? When the donor star is much smaller, or is there a mathematical point when it just clicks off?
Yeah. So the feeding essentially stops when the donor star no longer fills its Roche lobe. This is because the donor star and the accreting star, they're both still evolving throughout that period. So once the donor star has gotten rid of enough of its material, it will start to contract again under its own weight because it can now sustain the amount of gas that it has. So as a result, it contracts and it no longer fills its Roche lobe. So that's when the feeding
Mhm.
stops. Yeah.
Fascinating. The final bit is are you tending to use artificial intelligence now to analyze the spectra of those supernova candidates?
So I'm just going to repeat that question. Was
Yeah,
it,
I wondered if
do
you're
we
using
use, yeah,
AI for
yeah.
analyzing the candidates, the supernova candidates.
So there, in fact, one of my colleagues is indeed using machine learning programs to analyze spectra, in particular of type 1a supernovae, because we have a lot of data for this. So you can train your model to identify certain features and emission lines across these spectra. In addition to that, in fact, even the Kilonova Seekers project that I put the QR code for at the end of the talk, that also uses a machine learning model to sift through the large amounts of data. But we still need people to go through it because there's only so much that a machine can do.
Yeah, yeah. Okay, thank you very much again for the
Thank
presentation.
you.
Peter Floyd.
Yes, I hope you can hear me all right. I had some problems last week, but I think they're sorted. Yeah, and my question really follows on a little bit from that. Presumably, the orbits of the two stars around one another are not necessarily circular. So that made me wonder whether these transients come at regular intervals, sort of once every rotation.
That's an excellent question. Indeed, in cataclysmic variables, we get all sorts of flares, all sorts of outbursts. Some of them are very periodic. In fact, if you have read the news in the last few days or weeks, there's this cataclysmic variable system called T Corona Borealis, which undergoes outbursts very frequently, and I think about every 50 to 60 years. And the next outburst or the next brightening of this system is we know exactly when it's going to occur, and it's going to be anytime now up until 2026. The best window that we think it's going to occur in is between June and September, so like between now and September. And most of our telescopes are pointed at that specific star system because we think there's going to be an outburst. So in fact, so to answer your question, yes, we can track some of these systems because of their orbital periods. We can predict when they will flare next because we know how much matter how much matter is going from the donor star to the accreting star. So if we have the mass accretion rate and we have information on the orbital periods, we can calculate when the next outburst will be. But there are outliers to this. Some stars, they like doing their own thing, and we cannot predict exactly when they will go off because their mass accretion rate changes very rapidly as the star makes its way through its different layers. But some of them are very periodic, so yeah, we can definitely predict some of these.
Well, that must be very, very handy.
Very indeed.
Though, did you say every 50 or 60 years sometimes?
I believe so, yeah. So this particular system, T Corona Borealis, yes. And some star systems have outbursts which occur even at even shorter time scales. So like on the scale of a few days or a couple of
I was going
years.
to say, I was expecting you to say a few days because after all, the stars must be pretty close together when this happens. And I would have thought maybe
Yeah.
50 or 60 years seems an awful long time to go round.
Yeah. It all depends on the mass accretion rates as well. So how much matter is building up. So if it has a lower mass accretion rate, it will take much longer to build up that amount of matter, which will eventually explode in a thermonuclear runaway process.
Oh, well, thank you very much.
Thank you.
I'd like to just remind everybody that Corona Borealis is the club emblem. So it would be nice to get a picture of this supernova going off. So when you've got your sea stars and things out there, gentlemen, we'll just keep regular tabs of it.
Take a photograph of the region.
Right.
It's an anticipation.
Excellent. Inside the room, anybody got any questions?
Yeah,
Mr. Councillor.
while you're talking, I was wondering, these cataclysmic variables, you're talking about the white dwarf star being a smaller mass star than the donor star. But there are systems around, like Sirius, where the white dwarf is actually orbiting a larger mass star. I think Procyon is a similar system. What happens in that case? Because obviously that white dwarf's gone through a red giant stage. But if Sirius is an A-class star, shouldn't it be sort of have a shorter lifetime than what another white dwarf has?
So in cases where the white dwarf is accreting material from another giant star, in that case, the white dwarf has to be more massive because it attracts through gravitational fields the matter from the donor star. If I remember correctly, I think Sirius is it's a blue giant star, so it follows a different path of evolution, so it will never really become a white dwarf star because it started off its life as a much more massive star compared to the sun. So if you have a Sirius-like star which has a white dwarf orbiting it, then that supergiant star will be more massive than the white dwarf. So the white dwarf will keep orbiting it until eventually there will be a supernova. And it's unlikely that the white dwarf will survive the supernova when the giant star or when the supergiant star goes supernova, but in the odd case that it does survive it, what you will be left with is a neutron star and a white dwarf star orbiting around each other. Or in an even extreme scenario, you could have a black hole and a white dwarf star orbiting each other. But if the supernova leads to a black hole, it's very unlikely that the white dwarf star will survive.
Okay. Any other questions? I'm looking around the room one more time. I'm looking online. No other questions. Anwesha, thank you very much for a fascinating talk.
Thank you.
I ask everybody to join me in giving a big experience with the Astronomical Society. Thank you. Thank you very much.
Thank you so much. It was a pleasure speaking, and thank you for the excellent questions.